Yes, we can hear you. Go ahead.
All right, thank you. All right, okay, well, thank you for inviting me to make this presentation about TMT's capabilities to observe small bodies of our solar system. I'm really sorry I couldn't make it to this meeting, on site. So I have just a few minutes to give you like a lot of information about TMT and what we can actually do to observe solar system objects. So the plan, can you move to the next slide, please? I'm sorry. Yeah, okay. So the plan for this presentation is to give you an introduction about the project, TMT in general, and then I will move to more description about the capabilities that we will offer to observe small solar system bodies. Next. So this slide is just to give you an update on the current partnership of TMT. The current partners are India, China, Japan, Canada, and on the US side, we currently have the University of California and Caltech. The prime site of construction for TMT is Hawaii on top of Mauna Kea, not the very top, but just below the summit. This is our prime site, and we also have an alternate site in the Canary Islands. You can see that on the left side. And so we are going to start construction very soon in Hawaii, or resume construction very soon. And in case we encounter problems like in 2015 that will prevent us to move forward, we will actually switch to our alternate site. So I don't know if you're aware of this, but I'm pretty sure that you guys are. There is currently an initiative started to put together a US ELT program in collaboration with NOAO, GMT, and TMT. We are very excited about this, okay, because we will actually be able to provide the full sky coverage with 2 telescopes to the US community. And in particular for solar system scientists, this is very important because you can actually basically observe your target in the sphere you're on. Okay? So in a nutshell, what is TMT about? If you're familiar to observe with 8 to 10 meter class telescope of today's, then this is very similar in terms of instrument design and telescope design. It's altitude azimuth Ritchey-Chrétien telescope with 492 hexagonal segments to make a full 30-meter primary mirror. And the advantage of this telescope of TMT is that we can actually respond to very fast events. Okay, and we can swap instruments to move to a different target with a different instrument in the space of only 10 minutes. We can obviously track non-sidereal targets, including some NEOs, up to 15 arcseconds per second. And we will have, when we have the full suite of instruments, we will be able to offer 8 instruments in total on 2 national platforms. We will have a first light adaptive optics system called Nefarious, and so this will give us the opportunity to deliver fully diffraction limited images capabilities in the near infrared, GH and K-band and beyond. So we expect to restart construction, as I said, in a few months or in a few weeks from now, and we expect the first light to be in 2027, 2028. Next slide. Sorry, yeah, I forgot to tell you next slide. Okay, so you can switch there next. That was about TST, and I just spoke about this. Sorry. Okay, I was moving my slides on my screen, but not on your screen. Yeah, you can go to the next one. All right. Okay. Sorry about this. I'll try to do better next time. So this is the current timeline for the construction. As I said, we have access granted in Hawaii, just a few administrative steps away. So we should be able to. Can you go back one slide, because I think you went too far. Okay. Okay. No. So that I made a mistake. Go back. Go forward one slide. Sorry.
Okay. What's the slide title?
TMT Science Operation. Yeah. Okay. You got that. All right. Sorry about this. So because you are going to be future users of TMT, I wanted to give you like a quick snapshot of what kind of science operation support we will be providing. So we expect to implement all the science programs both in visitor mode and service mode, including supporting target of opportunities, eavesdropping. That means when you guys are actually connecting remotely from your institute or from home, and support the operation staff on the mountain or close to the mountain to actually do the observations for you. Be careful about visitor mode. We will adjust, okay, any science program to the current conditions on the mountain. So that means if you apply for visitor mode time on TMT, that doesn't mean that you will have a very fixed
Christophe, are you there? We seem to have lost audio here.
He's actually dropped.
He's dropped.
Yeah, his
Okay,
line disconnected. He was dialed in as a guest, so that's why he wasn't recognized earlier. He didn't have the leader passcode. I'm just waiting for him to rejoin.
Yeah, could you find him and message him? Okay, we'll just wait for him. Someone's trying to find and message him. Hopefully he'll call in shortly. Christophe.
Okay, I think he's dialing in now.
Okay.
One moment.
Okay, thank you.
He's got to get through the prompt, sorry.
About that. Okay. So just tell him to dial in. Dropped.
Okay. Your line is open, sir.
Okay, thank you. We were disconnected somehow, but the operator put me back on. Can you hear me?
Yes, we can hear you.
Okay, all right. So that's not a smooth presentation. Sorry about this. Hopefully we'll be more successful building TMT. So where I was, talking about science operation model. So I don't know where I was cut, okay, but we will provide visitor and service observing mode, including target of opportunity and eavesdropping. We will have a proposal cycle of about 12 months with fast turnaround. Okay, that's currently the plan. And all data will be archived, the raw calibration files, metadata. And we are currently talking with NOAO to actually provide also fully reduced data, okay, to the community, to the US community at least. Can you go to the next slide, please? All right, thanks. Okay, so this is just a snapshot of the construction timeline. If we are capable of resuming construction, I would say, in the next few weeks, in either Hawaii, which is our prime site, or La Palma, the alternate site, then we should be able to have first light in 2028. And by we call first light is actually having the adaptive optics system working with our one of the first light instruments called IRIS. I'm going to describe that to you later. And having like an enhancement of the image quality thanks to the adaptive optics system. Next slide. All right, so about science and instrument capabilities with the TMT for solar system bodies. Well, because TMT will be capable of switching very fast to any target, and we have a wonderful suite of instruments. You can do any kind of science you're currently doing today with 8 to 10 meter class telescope on a 30 meter class telescope, including supporting space missions and following up on LSST targets or JWST targets, for instance. So, we're looking at dynamical and compositional monitoring and mapping also, thanks to the high resolution, spatial resolution of TMT for any planetary surfaces of the atmosphere, studying the most primitive objects in our solar system and trying to understand or constrain better understanding of transport of the volatiles across the solar system. And as I said, observing time variable events, okay, because we'll be capable of having implemented target of opportunities. Next slide. All right, so performance expected in terms of sensitivity will be, basically about 150 times more sensitive than HST in seeing limited mode. But actually, if you take into account adaptive optics and observing point sources, we'll be actually able to be about 200 times more sensitive than the current PLTs. And in terms of angular spatial resolution, we do probably something like 12 times better than HST at 1 micron, and 3 to 4 times better than the current very large telescope 8 to 10 meter class. And on the right side, you can see some simulation of observations that could be made by the TMT to observe the Pluto-Charon system and also the Io Jupiter satellite. So in terms of Pluto and Charon, you can see that we can actually resolve both targets. And in the case of Pluto, actually, we could monitor the surface activities thanks to IFUs and a combination of imaging and spectroscopy. And for Io, this is a comparison of the TMT resolution on the right side at H-band with what we currently obtain in reflected light at H-band, not reflected light, sorry, in the H-band in 1.6 micron land with KKO. Next slide. All right, so this table just gives you an overview of, if you look at the numbers circled by red, okay, the number of resolution elements that we will actually be capable of obtaining by imaging some small bodies in the solar system. So if you take like objects like Ceres, which is the largest asteroid, we will have something like 130 resolution elements across the diameter of Ceres. If you look at the full disk, okay, then will be something like 17,000. So when you compare that to the VLT, which is the image down below on the left side, an image like that, like obtained for the VLT with some high contrast adaptive optics system like SPHERE, is quite comparable to what you actually can get with Dawn in orbit or in approach to Ceres. But we actually do 3 to 4 times better than that. Small objects like Triton, Chiron, Pluto, and Charon can also be observed and be resolved, so you can actually see details on their surface and actually even monitor surface activities. Like for Triton, for instance, you will have something like 20 resolution elements across the diameter, and you can actually monitor the activity of the plumes on the surface and geysers. Next slide, please. All right, so this is the discovery space of TMT in terms of instrumentation. Circled in green, the first light instruments, MODIS, the body force, and IRIS. On the right axis, on the x-axis, you have the wavelength, and the y-axis, spectral resolution. So you see that at first light, we will have like high spectral resolution in the near infrared, thanks to MODIS, and that will enable planetary surface and atmosphere compositional studies with a very high accuracy. You can also observe composition of small bodies in the solar system with IRIS, which will also be equipped with adaptive optics like MODIS, and between 1 and 2.5 micron, but at lower resolution, we provide imaging and spectroscopy. And the body force will be our first light workhorse instruments working with the visible. It will be a medium resolution spectrograph and spectroscopic observations of the surface of comets or asteroids can be done with this instrument, especially because it will go down to 0.3 to 0.31 micron. That means like in the long UV range, okay? And we are very interested in getting access to the window below 0.4 micron, where there are quite a few lines of interest on comets, for instance. So next slide. Yeah, so just the same one, but showing you that all these visible instruments like HPOS, which will be high resolution spectrograph in the visible, and W force will be seeing limited, providing image quality between 0.6 and 0.2 arcseconds, while the other suite of instruments like MODIS, IRIS I talked about, we provide diffraction limited down to 6 milliarcseconds, quite amazing. And we will have like PSI, which is a high contrast instrument, providing the best image quality that you can get on a 30-meter class telescope, in combination with spectroscopy. Next slide. So this is, just to let you know that all these instruments, except for IRIS, are at the very early stage of conceptual design. So it is time to join these instrument teams if you want solar system voices to be heard and want to make sure that your science requirements, okay, will be secured. Will be secured to actually, make sure to actually do the science you want to carry out with TMT. Next slide, please. All right, so just a timeline. Okay, start construction in 2019. First light with W force, IRIS, and MODIS. High spectral resolution, medium spectral resolution, the near infrared imaging and spectroscopy as well. because there was a push from the National Academy of Science to make a case that it is important to provide high contrast and high spatial resolution for planetary. Sorry, I got a call at the same time. I don't know what's happening. Let me just stop this. So to provide high spectral resolution and high contrast on 30-meter class telescope with funding support from NASA and NSF, we want to push very hard in having high contrast instruments and mid-infrared instruments capabilities to observe planetary systems very early on, around 2030, with then deployment of high spectral resolution in the optical, for instance, with HROS in the upcoming years. Next slide, please. All right, so this is just a quick snapshot of the kind of science you can actually do with TMT and what instrument you will need. So if you're interested in observing asteroids, searching for satellites and rings and characterizing them, so you will want to use an instrument like PSI, providing high contrast and high spatial resolution between 0.8 and 2 micron. It also provides spectral capabilities, so you can actually carry out the studies of all the components in your system. If you want to do 3D shape modeling, also the same thing, you will be using PSI. And surface composition, IRIS and MICHI will provide the full coverage between 1 and 15 micron. If you're interested in comets, then we also want to use MICHI, obviously, but also MODIS, which provides you this very high spectral resolution between 1 and 2.5 micron. And if you're looking at very faint objects at the end of our solar system, like Centaurs and trans-Neptunians, well, you will also want to use IRIS, okay, to get the spectral resolution and imaging at the same time. You will want to use WFOS if you're interested in fast photometry for occultation, for instance, and IRIS as well, because IRIS will have an imaging mode. Next slide. I'm almost done, okay? I have just 2 more slides. This is just a slide to illustrate, the power of modeling the shape of asteroids, okay, from the main belt with the current telescopes, and also observing very tiny objects around them, like rings around Chariklo, for instance, or Haumea. And so the combination of sensitivity and high spatial and high contrast, okay, provided by the TMT, will provide you an opportunity to do this science even better than it's currently done today. Next slide. All right. Okay. So another, topic of high interest will be to understand the transport of hydrated small bodies in the inner solar system. And so if you're interested in this kind of science, you will also be able to use IRIS and bodies in the near infrared to provide you medium and high spectral resolution, WFOS in the optical. And if you're interested in imaging these objects, you will need to use PSI or IRIS, which provide you the best spatial resolution in the near infrared. Next slide. All right, just to the final slide on science, okay, giant planets and satellites. Also, a strong interest will be to actually monitor the activities of satellites of the giant planets. So, for instance, iovolcanic activities or Europa surface in combination of in situ space missions. Obviously, okay, you can complement 30-meter class telescope studies with in situ space missions. And so, can you please move to the next slide? Yeah. Okay. So I have 2 more slides to conclude. I wanted to say that at TMT we do have what we call international science development teams called IDTs. More than 200 members across the world are actually part of these teams, representing any fields of science, including solar systems. And these people involved, and maybe some of you in this room, are actually part of IDTs. You can actually contribute to build the bridges between the TMT project and the science community by helping us organizing topical meetings like TMT forums, which are run annually, or attending DPS meetings and helping us attending the booths or make presentation over there. We basically, all these IDT members are helping us set the requirements to build the best instruments possible and making sure that we are going to operate TMT in the most efficient way for your science. So that another message, okay, so if you really want to make sure that solar system science is providing the best possible science with the TMT, you might want to consider joining an IDT for solar system, for instance, and be involved in the development of the future instrumentation for this telescope. Next slide. Yeah, so the deadline, there is a yearly membership access, okay, for IDTs, and the current renewal is ending on February 8th, so you can go to our webpage or send us an email at idt@tmt.org if you're interested to be part of IDT for solar system in particular. And the next slide will be the last one. Thank you. Yeah, next slide to conclude. Yeah, thank you. Okay, so just a schematic of the construction of the TMT while we are waiting for real images. Hopefully construction will start in a few weeks, few months from now. And next time I talk to the SBAG, I will be able to actually give you some real update on what's happening on the mountain. Thank you.
Questions in the room or online?
I wanted to ask about synergy with GMT. So is there anything particular that you're excited about in terms of TMT, GMT, for small bodies?
The question is, are there any particular synergies with GMT and TMT in regard to small bodies that you could talk about?
Well, you obviously have a synergy by having like a full sky coverage, okay, which that means depending on whether your object is observed in the northern or southern hemisphere best, okay, you can actually use one or the other telescope. In terms of instrument development, we are actually currently discussing this. All our first light instruments are already set, as I said, for W4, IRIS, and MODIS in our case. So we are not going to change that, but we are currently discussing with GMT the phasing of the next generation instrument, to have the best complementarity possible. Okay, an instrument like GMT, TMT, like our telescope, 30-meter class telescope, will be extremely good in the near infrared and thermal infrared and mid-infrared, providing superb high resolution, high contrast images using adaptive optics and laser guide stars. Of course, GMT will be capable of doing this, but GMT powers will also reside in providing a complementary coverage at shorter wavelengths with an overlap in the near infrared in terms of what you can do with the TMT. So there will be some complementarity and some overlap as well.
Thank you. Other questions? All right, thanks. Oh, one more. Yes.
I wanted to ask if there was any consideration for amount of time dedicated to planetary science or that's
Has there been any discussion of what fraction of the time on TMT will be devoted to planetary science?
No, absolutely not. And, basically, we know that if we can go along with the US ENT program, okay, that means the US community will have access of 25% on each of the GMT and TMT telescopes. But now, there is absolutely no discussion about solar system science versus exoplanet science versus, cosmology or any kind of science, okay? Basically, the proposals will be ranked according to the quality and the science impact of the science programs, okay? So the TAC will be autonomous, although TMT is an international partnership. Each partner will basically rule his own TAC and will be managing his own time, okay? So that's also something to consider. Only for very particular projects like large projects requiring long-term investment of observing time on TMT and or GMT, we will consider having like common TAC managing these special programs. Otherwise, all other programs will be managed in terms of assessment and implementation by the partner TAC.
Okay. Thank you.
Thank you.
Thank you very much, Christophe. And I believe we need to move on. The next presentation is going to